Chengchun. I'm currently an associate professor at the London School of Economics and Political Science. And today, it is a great pleasure for me to talk about the third part of our tutorial, which is about A/B testing. And we will cover methodologies for both policy evaluation and the design of the experiments. So I guess you guys must be familiar with A/B testing. It is like nowadays a very popular procedure used in various tech industries for the purpose of policy evaluation. So the goal here is to evaluate, is to compare two different policies. So in the second part of the tutorial, Tony has discussed several different methods to optimize, to compute an optimal policy. Now, once we have obtained those policy, now is the term to evaluate the performance of those policies. So typically, what A/B testing does is that to compare a newly developed policy, which we denoted as option B, against a standard policy, which denoted by option A. So here's the pipeline for A/B testing. So the first step is to design the experiment. And in this simple example, is basically to determine among those visitors who will receive the new treatment, who will receive the new policy, and who will receive the standard policy. And after we completed the design, we start the experiment, and then we collect the data. Based on the data, we evaluate whether the new policy is significantly better than the old policy or not. And finally, it's come to the product deployment. So we need to decide which policy to use at the end. So that's a standard pipeline, but you can also do it. You can also add some additional components to this pipeline. And so, for instance, during the experiment, so typically the data will come sequentially in order. So once you get some new data, you can use those data to further guide your experimental design. So you can apply the procedure sequentially. So once you determine the design, you collect the data according to this design. And then once you have some new data, you use this data to update your design and repeat this procedure. And similarly, at the policy evaluation step, so suppose we currently, based on the current data that we have, so suppose we can already tell that the new policy is significantly better than the old policy. Then we can just early stop the experiment for the purpose of saving time and budget. And there are some additional methods that you can use. For instance, you can incorporate historical data to enhance the performance of policy evaluation. And in this part, I will basically try to cover all these methods in the following 30 minutes. Now, let me give you some examples. So in this tutorial, we will mainly focus on the applications in ride sharing. So all three of us have working experience in ride sharing companies. So in terms of ride sharing, there are two types of policies of interest. So the first type of policy corresponds to those order dispatching policy. So it's basically like a matching policy. And in the second, again, in the second part, Tony has mentioned several different methods to optimize, to derive those optimal order dispatching policies. Now, the second type of policy corresponds to those subsidizing policies. And in the company, we have both driver side and passenger side subsidizing policies. So this figure visualizes an example of passenger side subsidizing policies. So basically, suppose if you open the app of those ride-sharing companies, so once you enter the destination, so there are some chances that those companies might send you some coupons to encourage you to order that particular ride for the purpose of balancing the demand and supply. So that's the second type of policies. Now, these two different types of policies, they have different approaches of evaluation. So as I will discuss in more detail later, so for those order dispatching policies, so typically we will randomize the policies are randomized over time. But for these subsidizing policies, the policies, they are randomized over the population. So let's first look at the order dispatching example. So for the purpose of evaluating newly developed order dispatching policy, so typically companies will conduct online experiments. And for the ride sharing company that we have working, so those experiments, they typically last for like 2 weeks. And given the 2 weeks, what we did is that we first discretized the data. So we discretized the 2 weeks into like 30 minutes time interval or 1 hour time interval. Okay? And then, as I have mentioned earlier, so for those, for the purpose of evaluating these policies, the randomization is conducted over time. So for certain 1 hour or for certain 30 minutes, we use like the new policy. For the rest of the hour, for the rest of 30 minutes, we use the old policy. And because of that, so the data that we collected forms a time series. And such experiments is typically referred to as time series experiments. And the data contains like two crucial components. So the first one corresponds to the observations that we observe at each of those like 30 minutes or 1 hour time interval. Okay? And it is typically a vector which contains like our outcome of interest, which can be either like the driver's total income within those 30 minutes or 1 hour time interval, or the number of completed orders. And additionally, typically we will also collect like the number of call orders and number of idle drivers within this 30 minutes and 1 hour time interval. So these two variables, they are known to have large predictive effect of the outcome of interest. So they serve as the supply and the demand of these two-sided markets. And because of that, when during the modeling procedure, we usually use like a joint modeling approach to simultaneously model all these three variables together to improve the prediction accuracy, as opposed to modeling only the outcome of interest. So that's the first part of first component of the time series, which corresponds to the observation. So the second component corresponds to the treatment. And for the purpose of A/B testing, so basically the treatment is binary. So we are interested to compare like the performance of a newly developed policy against an old policy. And our target of interest, the average treatment effect, basically corresponds to the difference in the average outcome between these two policies. So that's for order dispatching. And for subsidizing, it's very similar. So the only difference is that now the randomization is conducted over the population. So for some passengers, they will receive one subsidizing policies. But for the rest of the passengers, they will receive like another subsidizing policy. And because of that, the data that we collected contain observations from multiple individuals, and each passenger's data forms a time series. And again, we have like observations, and in this example, we have like both individual level observations, which are those observations associated with each of the passenger, as well as like those city level observations, including the demand and supply. And the treatment is again to compare like a newly developed subsidizing policy against an old one, and the average treatment effect is again the difference in the average outcome between these two policies. Okay, now here's the overview of my part. So it's basically divided into 3 sections. So in the first section, I'm going to talk about to discuss some of the challenges in A/B testing. Okay? And then for the second part, I will move on to talk about policy evaluation. So based on the data that we collected, how shall we estimate the average treatment effect? Okay? And finally, it's about the design of the experiments. So firstly, let's talk about the challenges. So here I list like 5 challenges, and I will discuss them one by one in the next few slides. So they correspond to the interference effects, partial observability, early termination, a small sample size, and weak signal. And finally, after that, I will also briefly give you some high-level ideas on how to address these challenges. So now let's first look at the first challenge. So the first challenge corresponds to the existence of the interference effects. So basically, and in those, typically in those two-sided marketplace, and in particular in ride sharing, so we have like 2 different types of interference effect. So first type corresponds to those carryover effects, or like the delayed treatment effects over time. So these effects, they typically appear in what I have mentioned as like those time series experiments where the treatments they are sequentially assigned over time. Okay? So that's the order dispatching example. So if you remember, so we assign different order dispatching policies over time. Now, essentially, what those carryover effects means is that the past treatments they are allowed they not only affect the past outcomes but the future outcomes as well. And because of that, many of the conventional A/B testing or causal inference methods would fail to capture those carryover effects. And later, I will give you a detailed example to illustrate like why to use rate sharing as an example to illustrate like why we have those carryover effects in these applications. And the second type of interference effects corresponds to those spillover effects. So this occurs at those like multi-unit experiments. Basically, the policy that you apply to a given unit, to a given passenger, for instance, it not only affects its own outcome, but the outcome of other passengers, the outcome of other units as well. And again, I will give you an example to illustrate like why we have those spillover effects in these applications. So firstly, let me give you like a very simple example to demonstrate like why we have those carryover effects they are likely to occur in two-sided markets. So again, we use this ride sharing as an example. So suppose here we divide the city into like 10 different regions. And suppose we have like 3 drivers in zone number 3 and 1 driver in zone number 10. Now at this particular time point, I suppose we have a passenger in zone number 6. So at this particular time point, we can consider like 2 different policies. So we can either ask one of the drivers in zone number 3 to pick up this passenger, or we can ask the driver in zone number 10 to pick up this passenger. So this corresponds to 2 different policies. Now, suppose if we use the closest driver policy, so we directly ask all the drivers in zone number 3 to pick up this passenger. And because of that, we will only have like 2 drivers left in zone number 3. Now, suppose sometime later in the future, we receive like 3 call orders in zone number 1. So in that case, of course, we can ask 2 of the remaining drivers in zone number 3 to pick up 2 of the passengers here. And we can also ask the remaining driver in zone number 10 to pick up the rest of the passenger here. But the problem here is that zone number 10 is very far away from zone number 1. So it might take a very long time for this driver to arrive at zone number 1 to pick up this passenger. And because of that, this passenger might refuse to wait and cancel the order. So in that case, we will miss one order in the future. Now, suppose we have the ability to travel back in time. Suppose we can do such kind of time traveling. So if we go back to this particular time point, so suppose if we consider a different policy. So instead of asking one of the drivers in zone number 3 to pick up this passenger, we directly ask the driver in zone number 10 to pick up this passenger. So the advantage of this policy is that it allows to save all the 3 drivers in zone number 3, so that when sometime later in the future, we are able to match like all of those 3 call orders in zone number 1. So this is just a very simple example to illustrate like why those carryover effects they are likely to exist in these like ride sharing companies. So you can see that how 2 different order dispatching policies at a particular time point they affect the futures in the future. And to summarize, in those applications, we have those carryover effects due to that the past treatments they are allowed to alter the distribution of the drivers in the city, which can in turn affect the future outcomes. So that's the carryover effects. Now the second, another type of interference effects corresponds to those spillover effects over space. So this basically refers to the effect of the treatment on other units' outcomes. And again, if you take the ride sharing example, to take ride sharing as an example, so these effects they are likely to occur for evaluating like subsidizing policies. So suppose a company is applying like different subsidizing policies at different locations of the city. Okay? And if you look at this example, so applying a subsidizing policy in one location, so will increase the order in this location. And because of that, it might check those drivers from neighboring locations to this location. Okay? And because of that, the policy, the subsidizing policy in one location not only affects its own outcome, but the outcomes of the neighboring locations as well. So leading to these spillover effects. So that's the first challenge, which corresponds to these interference effects. Now, the second challenge is about partial observability. So here, there are two figures. So if you look at the first figure, so the first figure visualizes the data collected from like a fully observable environment. So here, each of those OT corresponds to the observation. Each of OT corresponds to the observation. So basically, in this figure, so if the data is from a fully observable environment, then it satisfies the Markov assumption. So the data forms a Markov chain. So you can see that, for instance, you can see there's only one path from the past observation to the future observation. So there's only one path connecting these observations. And this path is being blocked by the current observation. And if you are familiar with those graph theory, so this basically implies that given the current observation, the past and the future, they are conditionally independent. And because of that, the Markov assumption is being satisfied. So that's the first figure. Now, but however, in reality, what we typically observe is data comes from like those partially observable environment. So if you look at the second figure, so here again, so ST still forms a Markov chain. But typically, what we can observe is not ST, but instead like a part of ST or like a noisy measure of ST, which we denoted as the observation OT here. And now, if you look at this figure, so you can see that there's a path from the past observation to ST-1 to ST+1 to OT+1. And this path is not being blocked by the current observation. So which means that, again, if you are familiar with those graph series, so this means that the past and future, they are conditionally dependent given the current observation. And because of that, the Markov assumption is being violated. So basically, the partial observability refers to the environment where the time series, where the data doesn't satisfy the Markov assumption. And typically, those partial observability, they are commonly observed in practice. So to illustrate, so here I visualize like two data sets collected from two cities in the ride sharing company. So there are 6 panels here. There are 6 panels. And each row visualizes the data collected from one of the city. Now, if you look at the first column, so the first column directly visualizes like the driver's income from those cities. So if you look at the first column, so you can immediately see that those data, they have very strong seasonal patterns. So during peak hours, we have like we get large driver's income, but like early in the morning, the driver income is very small. So based on the first figure, you can see, you can tell that the data have very strong seasonal patterns. Now, in the second and the third figure, so what we did is that we remove those seasonal patterns, and we also regress those drivers' income on other relevant market features to get the residuals. And then we visualize like the ACF plot and the PACF plot of those residuals. So for those of you that are not familiar with time series, so basically those ACF plot and PACF plot, they are widely used in time series analysis to visualize the properties, the autocorrelation structures of the time series. So from these plots, it tells us that the data doesn't come from like a simple autoregress process. For instance, at a lag of like 20 or 30, the PSCF value remains significant. And because of that, the data mustn't come from a simple autoregressive process. And because of that, the Markov assumption is likely to be violated based on this data set. So that's our second challenge on partial observability. The rest of the challenges, they are very easy to understand. So the third challenge comes from the need for early termination. So this is because the company typically have like a large number of policies to evaluate. And to evaluate each policy, we will need to conduct some experiment. And each experiment can take like a considerably long time. And because of that, early termination is very important for the purpose of saving time and budget. And the rest two challenges corresponds to the small sample size and the weak signal. So as I had mentioned earlier, typically those online experiments, they only last for 2 weeks. So suppose if we chop the data into like 30 minutes time intervals, so then we only get like 600 or 700 observations. Okay? So the sample size is small. And finally, even if we know that the new policy, they have some improvement, but if you look at these numbers, so the improvement will not be substantial. So typically, the improvement brought by the new policy ranges from like 0.05% to 2%. Okay? So this makes it extremely difficult to distinguish between the new and old policies. And to the contrary, please do not overlook these numbers. So although these numbers, they appear to be small, but if you take the total number of call orders the company have, so even like a 1% improvement or like a 0.05% improvement means a lot to the company. Okay? So even if the improvement is small, so we still need to decide, we still need to know like which policy will give us the better, will lead to better outcomes. And next, I just want to give you outline some solutions, give you some high-level ideas on how to address these challenges, and we will talk about the details later. Again, just want to remind you that the first challenge corresponds to the interference effect, and there are two types of the interference effect. So the first one corresponds to those carryover effects over time. And of course, there are many approaches that we can adopt to handle those carryover effects. But what I do want to highlight here is like one of those approach which proposes to use like reinforcement learning for A/B testing to handle those carryover effects. So in the second part of the tutorial, Tony has mentioned like how to apply reinforcement learning for policy optimization to compute the optimal policy. And here, what I want to argue that is that reinforcement learning is not only suitable for policy optimization, but it is suitable for policy evaluation as well. Okay? And in particular, there has already been like a few several papers that propose to use like a Markov decision process, which is widely used in reinforcement learning to model the experimental data generated from those online experiments for the purpose of A/B testing. Okay? So just want to remind you that in those MDPs, we model the data as like those state action reward triplets. So here, the policy corresponds to the action. So the action is binary. So whether either we use the new policy or the old policy, and the outcome corresponds to the reward. Now, if you look at this causal diagram of this MDP, so you can clearly see that there's a path from the past policy to the future outcome. So there's a path from the past policy to the future state to the future outcome. Okay? And because of that, if you use MDP, it allows to capture those carryover effects, those delay treatment effects using the dynamic system conditions. Okay? And basically, the past policies, they are allowed to alter to impact future outcomes indirectly through the future states. And in other words, the future states, they will serve as like mediators between the past policies and the future outcomes. Now, what it means to practitioners is that if you want to use this MDP framework, so when constructing the state, you probably do want to include those important mediators which will mediate the effects of the past policies to the future outcomes. And to the contrary, most existing solutions, they assume like all those observations, they are independent over time. And that's why like those A/B testing, classical A/B testing methods, they are not able to detect the carryover effects. They are not able to model to capture those delayed effects. Okay. So I have just talked about how to use reinforcement learning for A/B testing for the purpose of capturing the carryover effects. And in order to handle spillover effects, so very similarly, we can use like a multi-agent reinforcement learning framework for A/B testing. So the idea here is to like use a multi-agent model to model like each unit, each experimental unit by an agent. Okay? And because of that, under this model, those spillover effects across different units, they can be modeled naturally through the interactions among different agents in multi-agent reinforcement learning or MARO. Okay. And to handle the second challenge, which is about partially observable is about partial observability. So instead of using MDPs, you can also use like partially observable MDPs or POMDPs in reinforcement learning to capture those to address the second challenge. And again, there have already been like a few papers that use these models for A/B testing. And finally, the third challenge corresponds to early stopping. And to address this challenge, we can use sequential monitoring. So the idea here is that we can monitor the test. We can monitor the average treatment effect sequentially over time. So for instance, if you look at these figures, so here, this capital T denotes the total number of observations that we will receive after the experiment. So instead of conducting the experiment only at the end time point, we can also apply dual A/B testing like at some intermediate time points, such as at time point T1 and T2. Okay? But here, the key is that we probably do want to avoid a p-value peaking. So what it means is that suppose we conduct the test at like these three time points. So at time point T1, you set the significance level to be 0.05 and then do the test. Now, if it fails to reject the null hypothesis, so you wait until time point T2 and then apply the same procedure by again setting the significance level to be 0.05. And then if the test is again, if you are still not able to reject the test, you wait until the end point and do the test again. So this procedure is invalid because at each time point, you didn't adjust the type 1 error. You didn't adjust the type 1 error. You use the same significance level. And because of that, the total family-wise error rate so will inflate. It will be much larger compared to 0.05. So what you should do is to use like classical sequential analysis procedures such as alpha spending to adjust these significance levels at these intermediate time points in order to control the total family-wise error rate. And if you are interested, there's a famous book by Jonathan who give like who discuss the detailed alpha spending approaches designed for those sequential analysis. And finally, the last two challenges corresponds to the small sample size and weak signals. And in this slide, I listed like two potential approaches to address these challenges. So the first one corresponds to the design of the experiments. So that's a design-based approach. So that's how the design comes into play. Okay? So basically, what we can do is that we can carefully design the experiments to determine, like at each time point, during the experiment, whether we should use the old policy or we should use the new policy, so that after we collect the data based on this design, the AT estimator computed based on this data, it will achieve like the minimal mean square error. Okay? So that's the objective. That's the objective of experimental design. And in addition to experimental design, you can also consider other approaches such as data integration. Although the experimental data has like a relatively small sample size, but prior to conducting the experiment, the company had like a large volume of historical data. But prior to conduct the experiment, so the new policy has not been invented yet. And because of that, the historical data only contains observations associated with the old policy. So now, how shall we effectively combine the experimental data with the historical data to improve the estimation of the average treatment effect, cause effect estimator? Okay? And if you are interested, there are some recent works on this topic. So this concludes the first part of my talk. And next, we will move on to talk about policy evaluation. So based on the data, based on the experimental data that we have collected, how shall we evaluate the performance of a newly developed target policy? And in particular, so here I will cover like some classic policy evaluation methods, such as direct estimator, important sampling estimator, double robust estimator, and model-based estimator. And finally, I will also briefly talk about uncertainty quantification. So this is because A/B testing is naturally like a hypothesis testing problem. So it not only requires you to provide a point estimator, but you also need to produce the p-value. You also need to quantify the uncertainty of your point estimator. So when talking about policy evaluation, so in most of the times we will discuss we are referring to like off policy evaluation, where the goal is to evaluate the impact of a target policy offline using data generated by a possibly different behavior policy. And off policy evaluation is closely related to causal inference. So it's basically whose objective is to evaluate the difference between two drugs. And in the following, we will consider like three settings. So we start by talking about the simplest contextual bandit setting. So that's the simplest model. And under this model, there's no carryover effects and there's no spillover effects. And then we will move on to talk about the more general reinforcement learning setting, which allows to capture the carryover effects, but it doesn't address the spillover effects. And finally, we will briefly talk about the extensions to model, which allows to model like both carryover effects and spillover effects. So let's start with the simplest contextual bandit setting to illustrate the idea. So contextual bandits corresponds to like whether they use the model in medicine and also in tech industries. So it is very simple to describe. So the model basically can be described as follows. So at each time point, so basically the agent will observe like some contextual information. And then, based on this contextual information, the agent will choose an action. And again, in the context of A/B testing, so the action is binary. So either it is an old policy or a new policy. And after that, the agent will receive an outcome. Now, the objective is that suppose we are given like a ID sequence of those context action outcome triplets generated by possibly by a certain behavior policy. So here we use this function b to denote the behavior policy. So basically it tells us like what is the probability of choosing each action in the given context, given a contextual variable in the offline data set. So given the data generated by a behavior policy, we aim to estimate the AT, which corresponds to the expected outcome between the two policies. And there are now three common estimators available, which corresponds to the direct estimator, the importance sampling estimator, and the double robust estimator, which I will introduce in the next few slides. So firstly, let's talk about the contextual, the direct estimator. So to introduce the direct estimator, let me introduce like let us use this R to denote like the outcome regression function or the reward function, or in the terminology from the reinforcement learning literature. So basically, this R measures the conditional expectation of the outcome given the action and the context. Now, given this function, basically you can represent the ATE using this equation. So basically, it's a difference between the two reward functions. And you also need to calculate, and here the expectation is taken with respect to those contextual variables. Now, based on this formula, it motivates the direct estimator. So essentially, what we should do is that what this estimator does is that it first estimates the reward function. Using the historical data based on supervised learning. So basically, to estimate the reward, to estimate this conditional expectation, it is a regression problem. And once you have the estimated reward, you also need to like approximate this expectation using the empirical context distribution. And then you plug in these two estimator. You plug in these two estimator into this formula to produce the resulting ATE estimator. So that's the direct estimator. Now, the second estimator corresponds to the importance sampling estimator. So it requires to estimate the behavior policy again, using supervised learning. So just want to remind you that the behavior policy corresponds to the probability of choosing each action given the context, given the contextual variable. Okay? So you can use like classification methods to estimate those behavior policy. And once you have those behavior policy estimator, what IS does is that it constructs those important sampling ratio in order to adjust the distributional shift between the target policy and the behavior policy. So basically, that's the ratio. That's the ratio under a given target policy over the behavior policy. Okay? Now, what you have those IS ratios, what you can do is that you can reweight each of the observed outcome by these IS ratios. Okay? So this will gives you the unbiased estimator for each outcome under those target policies. Okay? And then you average these reweighted outcomes and take their difference to estimate the AT. So that's the basic idea behind those IS estimator. Okay? And in addition to this simple IS estimator, there are also some extensions of these IS estimators. So basically, it is known that when a behavior policy is small for certain action context pair, those IS estimator they might suffer from a large virus. And because of that, we can use like a self-normalized IS or like a truncated IS to address this issue to reduce this virus. Okay? And so far, we have talked about two different types of estimator, which corresponds to the directed estimator and the important sampling estimator. And generally speaking, there's like a bias variance trade-off between these two types of estimator. So the directed estimator suffers from some bias because the outcome regression function needs to be estimated from the data. And the important sampling estimator is unbiased if the behavior policy is known, but it might suffer from a large variance. So there's a bias variance trade-off between these two types of estimators. And next, I want to talk about like a very popular type of estimator, widely studied in the literature, and recently it has also been like widely applied in practical situations, which corresponds to those double robust estimators. Okay? So again, just want to remind you that so far we have talked about the directed estimator, we have talked about the important sampling estimator, and each of those estimators they require to estimate some function. So for the directed estimator, it requires to estimate the reward function. And because of that, its consistency requires consistent estimation of the reward function. Okay? And for IS estimator, it needs to estimate the behavior policy. And because of that, its consistency requires consistent estimation of the behavior policy. Okay? Now, essentially, what double robust estimator does is that it estimates both functions. So it estimates both the reward function and the behavior policy. And it turns out that it constructs the estimator in such a manner so that it requires a weaker condition to achieve a consistency. And in particular, its consistency only requires like one of the functions to be consistently estimated. So either the reward function or the behavioral policy can be consistently estimated. Then the resulting AT estimator will be consistent. Okay? It doesn't necessarily require like both functions to be consistently estimated. Okay? Basically, here's the detailed formula to construct those double robust estimators. So if you look at this equation, so basically there are two terms. Okay? So if you look at the first term, so the first term essentially corresponds to the difference in the two reward functions. And as I had mentioned earlier, so this basically corresponds to the estimating function in the directed estimator. So if you remember, for the directed estimator, what it does is that it directly takes the difference between those two reward functions to derive the AT estimator. So that's the first term. Okay? And the second term looks a bit complicated, but it basically corresponds to an augmentation term, which relies on the important sampling ratio. And the purpose of adding this second term is to debias the bias of the directed estimator, which offers additional robustness properties against the model misspecification of the reward function. Okay? And once you have this estimating function, what you can do is that you can average this estimating function over those context action outcome triples in the offline data in order to estimate the AT. Okay? So that's the double robust estimator. And next, I just want to talk about some of the properties of those double robust estimator. So the first property corresponds to the double robustness property. So basically, you can verify that. So this slide basically tells you you can verify that if the reward function is correctly specified, then the double robust estimator will will be approximately equal to the direct estimator, which is of course consistent when the reward function is correctly specified. Okay? But suppose when the behavior policy is correctly specified, then you can also show that the resulting direct estimator it is asymptotically equivalent to the importance sampling estimator, which is again of course consistent when the behavior policy is correctly specified. So this verifies the double robustness property of this estimator. So it is consistent as long as like either the reward function or the behavior policy is consistent. So the second property is about the efficiency. So essentially, suppose if we know that the behavior policy is correctly specified, then the resulting estimator is unbiased. And then in that case, if we know that the reward function, additionally, if the reward function is also correctly specified, then you can basically show that the resulting estimator it achieves the minimal variance. So what it tells us is that in practice, when the behavior policy is correctly specified, a good working model for the reward will improve the resulting estimator's estimation accuracy. Okay? And indeed, in theory, you can show that the resulting estimator, if both functions are correctly specified, then it achieves the efficiency bound. It means that it achieves the smallest mean square error among a class of estimators. So that's the second property about efficiency. And the third fact is again about efficiency. So this is a very interesting fact. So basically, it tells us that if suppose the behavior policy is estimated from the data, and if the model used to estimate the behavior policy is correctly specified, then very interestingly, if you estimate the behavior policy to construct an importance sampling estimator, then its mean square error will be smaller than or equal to the mean square error of the importance sampling estimator with an oracle with the true behavior policy. So this result is like a bit counterintuitive. So typically we will assume that if we estimate something, that it will make the performance worse due to the estimation error. But here, when estimating the behavior policy actually yield like a more efficient estimator, even if in cases where we know the oracle behavior policy. So this phenomenon has been discovered and has been well studied in the classical statistics literature. And recently, there are a few papers that shows that the same finding also holds true in reinforcement learning. So in reinforcement learning, you can also construct like those importance sampling estimators, and they show that basically the MSE of the resulting importance sampling estimator they can be reduced through history-dependent importance sampling, and the longer the history length, the smaller the variance. So finally, the last property is about asymptotic normality. So this is a very desirable property for those estimators. So as I have mentioned earlier, so A/B testing is essentially like a hypothesis testing problem. It is a statistical inference problem. So you not only need to know what is the point estimator, but you also want to provide the uncertainty quantification. And asymptotic normality is like a desired property where you can use normal approximation to quantify the uncertainty of your estimator. So essentially, it tells us that if those the double robust estimator will converge at a parametric rate, which is the root n rate, and it remains asymptotically normal, even when the estimated reward function or the behavior policy they converge at a much slower rate than the parametric rate. And this enables us to apply like modern deep machine learning methods to estimate like both the reward function and the behavior policy, which leads to like the famous double machine learning estimator, which has been widely applied in different applications. And there are also like extensions of those double machine learning methods to reinforcement learning. Which I will also discuss a few slides later. So they were like those double reinforcement learning estimators that generalize this DML to RL settings. Okay, so far we have talked about introduced those estimators in like the simplest contextual bandit setting. Now let's move on to talk about those estimators in a more complicated reinforcement learning setting. Okay. And here, let's focus on the MDP model. So assuming the Markov assumption can be satisfied, so assuming the state variable can be fully observed. And our objective is very similar. So given an optimal data set, now in reinforcement learning, just want to remind you that those for those data, they are typically summarized into like those state action reward next state tuples. Okay? So given a set of those tuples generated by a behavior policy, so again denoted by B, we wish to estimate the average treatment effect estimator. And here, the AT corresponds to the difference in the expected return between the two policies. And here, the return corresponds to the cumulative of the reward. So this is because we consider like this sequential, this dynamic setting. So we are not only interested in the reward at a given time point, but the long-term reward, the cumulative reward over time. And here, gamma basically denotes the discount factor, and you can also set gamma to be equal to 1 in those finite horizon settings. So basically, it's the sum of the return basically then becomes the sum of those rewards. And very similarly, you have like a direct estimator, you have the importance sampling estimator, and you have double robust estimator. So those are versions of these estimators developed under the reinforcement learning setting. And finally, I will also briefly introduce the model-based estimator. So let's first look at the direct estimator. So it is very similar. It is very similar to the direct estimator introduced in the contextual bandits setting. If we use this V to denote the value function, which corresponds to the expected return starting from a given state, then very similarly, you can show that the AT estimator it can be represented as like the difference between two value functions. Okay? So here the value functions measures the long-term reward. The expected value of the long-term reward as opposed to the immediate reward. Okay? And the direct estimator is very simple. It is very similar to the one developed in the contextual bandit setting. So basically, it estimates the value function using like existing reinforcement learning algorithms such as like fitted value or Q evaluation, or like you can also use like least square temporal difference learning or like kernel-based methods. There are several IL algorithms available to estimate the value function. And once you have the value function estimator, then you also need to approximate this expectation. You also need to approximate this expectation using the empirical initial state distribution. And then you plug in this estimator into this formula to construct the resulting AT estimator. So that's the version of the direct estimator in the reinforcement learning setting. And the second estimator is again like the importance sampling estimator. But here, in the reinforcement learning setting, in the sequential setting, there are like two types of those importance sampling estimators. So the first one corresponds to those sequential importance sampling estimator. So it's very similar to the IS estimator in the contextual bandit setting. It also requires to estimate the behavior policy using like classification or supervised learning algorithm. And then the difference lies in that at each time point, now you will need to reweight the reward, not only using the importance sampling ratio at that particular time point, but you should use like a product of those IS ratios from the initial time point, to time point t to time point t to adjust like all those distributional shifts encountered at these t time points. Okay? So this is because under this settings, the past actions they can also affect the future outcomes. Okay? And because of that, you need to use the product of those ratios to adjust for all those delayed treatment to adjust for all those distributional shift for those delayed from those past actions. Okay? And once you have those importance sampling ratios, so again, you average these reweighted rewards to estimate the average treatment effect. But the limitation of those sequential importance sampling estimator is that it suffers from the curse of horizon, which means that basically, if you calculate the variance, of this sequential importance sampling ratio, the variance of the product of these ratios, it will grow exponentially faster with respect to capital T. So this estimator it suffers from a large variance, and there are also extensions of those sequential importance sampling estimator to like those double robust estimator, but they still suffer from a curse over horizon. And the second type of importance sampling estimator corresponds to those marginalized importance sampling estimator. And these estimator they are being proposed to address to overcome the curse of horizon. So what it does is that it takes the structure of the problem. So it employs the Markov assumption to break the curse of horizon. Okay? So essentially, you know that at each time point, the reward is conditionally depends only on the current under the Markov assumption. At each time point, the reward depends only on the current state action pair, and it is independent of the past data history. And because of that, at each time point here, you just need to reweight the reward using the marginalized importance sampling ratio, which is now a ratio of both the state and the action. Okay? So if you look at the IS ratios in the first equation. So in the first equation, it only considers the IS ratio of the actions given a state. Okay? But here, if you look at the second equation, so here we calculate the ratio of both the state and the action. Okay? So essentially, if you take the distributional shift of the state into consideration, then it turns out that you only need to use like this ratio at time point t to adjust for the distributional shift. So there's no need to multiply the ratios from the previous time points. Okay? And this substantially reduces the variance of the resulting AT estimator. Okay? And these marginalized importance sampling ratios, they can also be computed via some existing algorithms, such as like minimax learning or RKHS based methods. And the third estimator corresponds to the double robust estimator. And here I want to mention like a particular type of double robust estimator, which corresponds to those like double reinforcement learning estimator. So as I have mentioned earlier, so this double RL, they basically extends like the double machine learning estimator developed in a contextual bandit setting to the reinforcement learning setting. Okay? And if you look at this equation, so basically its formula is very similar to the double robust estimator in the contextual bandit setting. So the estimator can basically be written as a sum of a direct estimator plus an augmentation term. Okay? And this augmentation term will rely on the marginalized importance sampling ratio, which I have just talked about in the previous slide. And its purpose is very similar. It is to debias the bias of the direct estimator, which offers additional protections against the model misspecification of the Q or value function. Okay? And very similar, you can show that this double reinforcement estimator, it is double robust. So it is consistent when either the value function or the MIS ratio is correctly specified. And it also achieves the same the efficiency bound in MDP problems when both Newton's functions they are correctly specified. Okay? And it is asymptotically normal when both Newton's functions they converge at certain rates. And finally, I just want to highlight that in addition to this double reinforcement learning estimator, so there exist efficient direct and MIS estimators as well. So not only can double RL achieve the efficiency bound, but the direct estimator and the marginalized importance sampling estimator can achieve the efficiency bound as well. Okay? And in particular, you can show that, for instance, if we use like a linear function approximation or kernel-based methods to derive those direct estimator, then the resulting estimator they are efficient. They can achieve the efficiency bound. And for MIS estimator, so if you use linear function approximation, then you can show that basically the resulting estimator is the same as the double reinforcement learning estimator, and because of that, it achieves the efficiency bound as well. So far we have talked about like how to produce like point estimators for the average Riemann effect, but less has been considered regarding uncertain quantification. Okay? And here's a follow-up work for the double reinforcement learning estimator, where we propose like those deeply debiased policy evaluation methods. So the goal here is to not only to provide the point estimator, but to produce a valid uncertain quantification so that we can produce valid p-values for the purpose of A/B testing, for the purpose of hypothesis testing. Okay? And basically, I suppose if you only wish to provide a point estimator, then you typically need to make sure that the bias and the standard deviation of this estimators, they are approximately of the same order for the purpose of minimizing the mean square error. But for the purpose of uncertainty quantification, you need to make sure that the bias decays at a much faster rate than the standard deviation. So that's why we propose such like a deeply debiased procedure, which iteratively debias the bias of the value function estimator. And it guarantees that if you apply this debiasing procedure like sufficiently many times, then the bias of the resulting estimator it will be much smaller compared to the standard deviation. And because of that, the resulting p-value, the uncertainty quantification procedure becomes valid. And finally, so far I have focused on talking about like those direct estimator, the importance sampling estimator, and double robust estimator. And all these estimators, they correspond to like model-free estimators. And in addition to using those model-free estimators, you can also consider to use like a model-based estimator. And under an MDP model, so what it does is that it basically estimates this MDP model, which requires to estimate like the reward function and the state transition function. So basically, like what is the conditional expectation of the reward given a state action pair? What is the probability of like transiting into a future state given a current state action pair? Okay? And once you have the estimated MDP model, then you can use like existing policy evaluation methods. There are several like dynamic programming or Monte Carlo method or temporal difference learning for the purpose of policy evaluation. Okay? This corresponds to their backup diagrams. And if you are interested, you can take a look at Sutton's book for a detailed treatment of these classical methods. Okay, so far we have talked about like how to produce how to provide like point estimator to estimate the ATE, and this slide basically summarizes some existing procedures for uncertainty quantification. So not only to provide the point estimator, but to estimate its standard deviation or to construct the confidence interval. So basically, if you look at this table, if you look at these rows, so it classifies these methods into 4 different types. So either using like concentration inequality, or based on like normal approximation, or using bootstrap or empirical likelihood for the purpose of uncertainty quantification. Okay? And if you look at these columns, so these methods, they can be further categorized into 4 different subtypes. So depending on like which type of estimator it uses to estimate the average treatment effect. Okay, so you can also use like either model-based method or direct estimator, importance sampling estimator, or double robust estimator to estimate the AT while providing valid uncertainty quantification. Okay, so finally, so far we have talked about like classical off-policy evaluation methods designed in the reinforcement learning literature, developed in the reinforcement learning literature, and recently there were some proposals that there were some recent proposals that recently developed for A/B testing under certain conditions. So in particular, this paper by Ferris, they proposed like a difference in Q estimator, which is valid under the assumption of weak carryover effects. So it does allow the carryover effects to exist, but on the other hand, it requires the size of this carryover effect to be small. Okay? So basically, this difference in Q estimator, it can also be viewed as a direct estimator. But when compared against like other direct estimators, so this DQ estimator is like an on-policy estimator, which calculates the difference in the Q estimators under the behavior policy, under the policy that generates the experimental data. But in comparison, like most direct estimators studied in the reinforcement literature, they are off policy in nature. They calculate the Q function estimators under the target policy. Okay? And it turns out that there's a bias variance trade-off between these on-policy estimator and the off-policy estimator. So basically, those on-policy estimator, they will achieve like a much smaller virus. But of course, there's no free lunch, so they suffer from like a larger bias compared to those off-policy estimators. But the order of the bias depends on the size of the carryover effects. So in settings where the carryover effects is small, then you know that this bias is small. But to the contrary, like this on-policy estimator, it can achieve like a substantial reduction in the variance. Okay? And in settings where the carryover effects, they are small, they are weak, those on-policy estimator, they will be preferred over the off-policy estimator for the purpose of variance reduction. And so far, we have talked about policy evaluation in MDPs, but there are also policy evaluation methods available in partially observable MDPs. And you can either use like a model-based methods based on like a linear state-based models, or there are model-free methods available using the notion of future-dependent value function. Okay? And all the previous discussion focus on like a single agent reinforcement learning, single agent setting, but there are also extensions to models to multi-agent settings. So basically, in these settings, you can apply the mean field approximation designed for policy optimization to OPE. And you can also use like those permutation environment or graph neural networks to model to handle the challenge of about the spillover effects. So this concludes the second part of the talk, which is about policy evaluation. So finally, let me move on to discuss the last part, which is about the design of experiments. So we will start by talking about discussing some classical designs and discuss their trade-offs. And then we will provide like a selective review of some recently developed optimal designs. And finally, we will conclude by discussing a case study in ride sharing. So firstly, I just want to recap about the order dispatching problem. So I have talked about this example at the beginning of the third part of our tutorial. So just want to remind you that the goal here is to evaluate the performance of a newly developed order dispatching policy. Okay? And again, during the experiment, this toward that end, to evaluate those policies, like the experiment, they typically correspond to a time series experiments where we discretize the entire experiment into like 30 minutes or 1 hour time interval. Okay? And this time series, it contains like two components. The first one corresponds to like an observation vector. The second one corresponds to a binary treatment. Okay? And our goal is, again, the average treatment effect, which corresponds to the average outcome, the difference in the average outcome between the new and old policies. Now, if you look at this figure, so just want to remind you the objective of the design problem. So basically, our goal is to determine during the experiment, during this time series experiment, at each time point, whether we should use the old policy or whether we should use the new policy. So that after we conducted this experiment based on this design, the AT estimator computed based on this data, it will achieve the smallest mean square error. Okay? So that's the purpose of the experimental design. Now, in terms of the design, so let me introduce like some very simple designs that we can consider. So the first design corresponds to those like alternating day design. Okay? So if you look at this design, it is very simple. So basically, in the first day, we apply the old policy. And then on the second day, we switch to the new policy. Okay? And then day number 3, we switch back to the old policy, so on and so forth. Okay? So that's a very simple alternating day design, or AD. Now, the second design is very similar to the first design, but the difference here, it corresponds to the alternating time design. But the difference here lies in that, so similar to AD, it also switches the two policies back and forth. But here, the difference lies in that it switches the two policies in a much faster, in a much frequent manner. So instead of switching those policies on a daily basis, so here we switch the two policies like every 30 minutes or every 1 hour. Okay? So it is very similar to the first design, but the major difference lies in that the switches they are conducted more frequently. So now here's a question. Here's a question for you guys. So now I have introduced like two designs, the AD design and the AT design. So which design do you think is better? Which design do you think is better? So if you think AD is better, raise your hand. Okay, if you think the second design, AT is better, raise your hand. So I guess most of you know the answer. But what I do want to highlight here is that basically the two designs, they have their own advantages. So for the first design, for AT, basically the advantage is that it is an on-policy design. So which means that within each day, it assigns the same treatment. It assigns the same treatment within each day. And this pattern is consistent with the definition of the AT. So if you think about the definition of AT, we are also interested to know like what if we within each day, what if we use like either the old policy or the new policy? Okay? And there are some benefits of using those on-policy design. Basically, it allows to avoid those distributional shift. And we can also show that those on-policy design, they are optimal. They are optimal in Markovian environments. So if the data that satisfy the Markov assumption, then the on-policy design, they are optimal. Okay? But to the contrary, like the second design, those AT, they are we can see that they are widely used in practical situations. They are widely used in several ride sharing companies. And I also have like a collaborator, an industrial collaborator. And according to my collaborator, they told me that the second design, which is AT, it will often lead to like a less variable AT estimators compared to the first design. Okay? And in the next few slides, I just want to briefly explain like why the second design can be more efficient compared to the first design. Of course, there are like many possible explanations available, and here I will focus on offering one of them based on from the perspective of partial observability. Okay? For illustration purpose, let's consider like the simplest bandit example. So if you look at the first equation, so this is like a very simple bandit model. So basically at each time point, suppose if we use the old policy, then the average outcome will be equal to A. And if we use the new policy, then the average outcome will be equal to B. So here, E corresponds to some mean zero errors. So this E corresponds to some mean zero errors. Now, under this simple bandit setting, so you can show that basically the AT corresponds to the difference between A and B. And it can be basically estimated using simple sample mean estimators. Okay? So you just average like the outcomes under these two different policies and then take the difference. Now, if you calculate the resulting estimators mean square error, so you can show that the resulting MSE under the two designs, they are equal to these two expressions. Okay? Now, so if you look at the first, so again, just want to remind you that this ET, they correspond to the residuals. They correspond to the residuals at a given time point. Now, if you compare these two expressions, so it is clear that the effectiveness of these designs, they depends on the residual correlation. So if the residuals, they are uncorrelated over time, then both designs, they will yield the same mean square error. Okay? But suppose the residuals, they are positively correlated. Now, due to that, the first design, the AD, it assigns the same treatment within each day. And because of that, it will lead to the inflation of the AT estimators variance due to the accumulation of those positively correlated of those positive correlations. Okay? But to the contrary, since the second design, AT, it alternates the treatments for adjacent observations. And because of that, it effectively like those residuals, they will cancel out with each other. So that's why the second design will lead to like a more efficient AT estimator. Okay? Under with positively correlated residuals. And finally, if the residuals, they are negatively correlated, then of course AD it will performs better compared to AT. Okay? So based on our previous discussion, so we have showed that the second design, those AT, it can be better when the residuals, they are positively correlated. Now, what I do want to highlight here is that those positively correlated residuals, they are commonly seen in practical situations. So here, so I show you like two figures. So in these two figures, it basically visualizes like the correlation of those residuals. So here, red means a red color means the residuals they are positively correlated, and the blue color means the residuals they are negatively correlated. So if you look at these two figures, so you can see that the majority of the residuals there exists like a large proportion of the residuals that they are positively correlated. Okay. And also, I want to highlight that if the residuals they are positively correlated, then this means that we must work with a partial observable environment. So this is because if if the Markov assumption is satisfied, so suppose if we work with a fully observable environment, then the data satisfies the Markov assumption under which the residuals will be uncorrelated. Okay? And because of that, positively correlated residuals they can only be met under partial observability. Okay? So this also suggests that in real practice, partial observability is more realistic. Okay? So far we have considered like a very simple analysis which excludes the carryover effects, which considers like a very simple banded settings. But in more general setting, when there exist those carryover effects, so it turns out that there is the trade-off. There is a trade-off between like those on-policy designs and off-policy designs. So basically, if the carryover effects is large, then those on-policy designs they will be favored in order to avoid those distributional shift. But if like the residuals they are positively correlated, then those off-policy designs they will be favored for the purpose of variance reduction. So there exists a trade-off between those on-policy and off-policy designs in general. Okay, and here's a practical workflow to indicate like which of those designs that we should use in practical situations. So for instance, so firstly we need to assess the size of the carryover effects. So if the carryover effect is large, then we probably do want to use those on-policy design to avoid distributional shift. Otherwise, we look at the correlation. So if those residuals they are positively correlated, then we probably do want to use like those off-policy, like switchback designs. Otherwise, those on-policy designs they will be preferred. Okay, so far we have talked about like those time series experiments where there's only like a single unit in the experiment and the humans they are sequentially assigned to this unit. But if you consider like subsidizing example, there are also like those multi-unit experiments which involves like multiple subjects, which involves like multiple like passengers in the experiment. And in this setting, so very similarly, there are like multiple different designs that we can consider, like including the global design, the individual design, and the cluster randomized design. So very similar to the time series, to the case of time series experiments. So there's generally like a trade-off among these three different types of the designs. So basically, those global design they are on-policy design, and they will be favored in settings with large spillover effects for the purpose of avoiding those distributional shift. While for those individual designs, they are off-policy, and they will be preferred in settings with like positively correlated residuals for the purpose of variance reduction. So this is very similar to the trade-off of like on-policy and off-policy designs that I have just mentioned in those time series experiments. Okay? And for these multi-unit experiments, so typically in the literature, people prefer like those cluster randomized designs. So which instead of using like individual design or global design, it lies in the middle. So basically it groups like those different spatial units into clusters. Okay? And then assign ID policies to those clusters. So here I list some references. If you're interested, you can also take a look. And next, let me briefly talk about give you a review of some optimal recently developed optimal design. So all of them are designed for like those time series setting for those time series experiments. Okay? So the first one corresponds to the MDP design, and there's code available. And we will post the slide, so you should be able to have access to these GitHub links. So this design is optimal, can be shown to be optimal in Markovian environments. So basically, if you look at this figure, so this figure visualizes like three different models. And the last two models basically corresponds to those MDP models. So depending on whether it is like a time varying MDP or like a time invariant MDP. Okay? And the first model corresponds to like a non-MDP model, where basically the reward and the state transition state depends on all the past history. Okay? And it turns out that such a design is optimal in all of these three settings when applied to all these three models. So what it does is that it uses like the double bust method that I have just talked about in a second part to estimate the ATE. And this design is like an on-policy design. So you basically within each day it assigns the same treatment, and across days it switches the treatment, and it uses like a Newman allocation. So basically, the number of days assigned to the treatment and the control, they are proportional to the variance of the daily returns. And the second design corresponds to an optimal switchback design proposed by Boyanov and his collaborators. So basically, they showed that their design is minimax optimal. Their design is minimax optimal among the class of regular switchback designs. So if you look at these figures, so basically, this regular switchback designs, it corresponds to a restricted. It is a restricted class of the designs. So if you look at the first figure, so for instance, among all possible designs, only these four belong to the class of regular switchback designs. So they consider a restricted class of designs. And the potential limitation of this their method is that they propose to use like sequential importance sampling to estimate the AT, which I have, according to what I had mentioned earlier, it might suffer from the curse of horizon. Okay? And this design is those switchback designs. They are typically like off policy designs. So within each day, they will switch. They will switch between the two policies. So each policy is implemented for a specific duration, and then switch to the other. Okay? And they show that the optimal randomization frequency aligns with the order of the carryover effects. Okay? And finally, there's a recently proposed ARMA design, so which is proven optimal in those partially observable environments. So here, what this also does is that they propose to employ like classical time series models, like very classical ARMA models, to model the observation data, and then to derive the AT estimator, and then to develop the optimal design. So if you look at their model, so their model contains like three parts. So there's a like auto-regressive part. There's an auto-regressive part to model the observations. So basically, if you look at the blue part here, so each of the observation, they will be affected by the past observations. So this corresponds to the auto-regressive part. And they also propose like a moving average. There's also like a moving average model for the residuals. So if you look at this purple part, okay, so they assume the residuals they have like a moving average structure. And finally, they also have like a control component in order to incorporate the policies. Okay? So they use simple time series models, and it turns out that although these models they are simple, they are very it is also powerful in a sense that it allows to simultaneously capture carryover effects and partial observability. Okay? And in theory, these sources they establish the asymptotic and mean square errors of those AT estimators for the purpose of compare different designs. And then in terms of optimization, they also propose like a reinforcement learning algorithm to compute the optimal design. Okay? And finally, I just want to show you a case study to compare all these designs that I have just mentioned earlier. So here we conducted, and the code is available. So again, we will post the slides so that you can have access to the code. So here we consider like three experiments. So in the first experiment, we use like a very simple dispatch simulator. So this is basically like a simple ride sharing environment over a none-by-one spatial grid. And this is also used in the paper by Xu ETAL. So in this environment, so the target policy corresponds to the MDP order dispatch policy, and the old policy corresponds to the distance-based policy. Okay? And if you look at the performance of these estimators, so here AT and AD corresponds to those classical the two basic designs that I have mentioned earlier. So UR corresponds to like a uniform random design, which at each time point it use like a Bernoulli random variable to generate those treatments. And greedy corresponds to the Ipsum greedy design, which is commonly used for policy optimization. And switch corresponds to the optimal switchback design that I have talked about earlier. And this TMDP and NMDP corresponds to the MDP designs. And the last two they correspond to the ARMA design, which I have just talked about in the previous slides. Okay? So you can see that the last design, the ARMA design, achieves the best performance. And for the second experiment, so here we use we consider like a city level or real data based simulator, which divides the city into 85 different regions. And the orders and the drivers, they are all generated based on historical data set. And again, you can see like the ARMA design, it achieves the best performance. And finally, we also conduct some real data-based analysis. So using data from a ride-sharing company. So this is how the data looks like, and we conduct some bootstrap-based simulation and to compare the performance of those different designs. And you can also see in general, generally speaking, like those ARMA design, they achieve the best performance. They achieve the smallest mean square error. So that's all for my part. And as Tony mentioned, we will upload the slides so you can have access to all these reference and the GitHub links for our code. Okay, thank you. So now let me move. Let me stop share. So Tony, do you want to continue?
Do we want to take a break for like 10 minutes, maybe?
10 minutes. So let's have a break for 10 minutes, and then we will continue.